Hey everyone, and welcome back for another deep dive.
Always exciting to be back.
Today, we're going to be tackling something that's, well, it's a real head scratcher.
Yeah.
It's this whole relationship between pressure and information density and gravity, you know. And you guys sent in some fascinating research on this.
Yeah, really interesting stuff.
So we're really excited to dive into this with you today, and we're going to be talking about some pretty paradoxical stuff here.
Yeah, it really does kind of turn everything on its head a little bit.
Yeah, like if it flows from low to high density,
Yeah.
why doesn't high pressure flow to lower pressure?
Right, exactly. Yeah, and how can black holes have such low internal pressure when they're so incredibly dense?
Right.
It's a real puzzle.
It is. It is. It
Yeah.
really makes you question a lot of assumptions about how we think about the universe.
Absolutely, yeah. It's like looking at the familiar through a kind of cosmic funhouse mirror.
I love that. I love that analogy.
Yeah.
Okay, so before we journey too far down the rabbit hole here,
Right.
let's define some terms.
Yeah, good idea.
We're talking about pressure, information density, and gravity.
Right.
Just, light topics.
Easy stuff, casual, everyday things.
Yeah. What? I mean, where do we even begin with these?
Well, I think a good place to start with pressure is to think of it as the force exerted over a certain area.
Okay.
And it really comes down to how much stuff is packed into a space
Okay.
and how much that stuff is kind of jostling around.
Oh, okay. So like a crowded subway car at rush hour.
Like exactly.
Lots of jostling going on in there.
Lots of jostling. Yeah, that's a great analogy.
Okay.
And then when we talk about information density,
Yeah.
it's really about how much information is packed into a given space.
Okay.
It's a way to kind of measure the complexity and order of a system.
Got it.
So you can think of a system with high information density
Okay.
as being like a well-organized library
Okay.
where everything's easily accessible, interconnected.
So my email inbox is the opposite.
Yeah, exactly.
Okay. Got it.
Low information density, high stress levels.
Yeah, pretty much.
And then, of course, we have gravity,
Right.
which we experience every day as the force that keeps our feet on the ground.
Keeps us grounded, literally.
Literally, yeah.
Okay.
But in the realm of Einstein's general relativity,
Right.
gravity is actually a manifestation of information density itself.
Okay.
So the more mass and energy that are concentrated in a region of space, the more space-time curves.
Right.
And that curvature is what we experience as gravity.
It's like more stuff literally warps the fabric of reality.
It really does, yeah.
Okay.
It's a mind-blowing concept when you think about it.
It is.
Yeah.
Okay. So I'm starting to see how all of these kind of connect with each other.
Yeah.
But then we bump into this paradox.
Yeah.
Gravity pulls things together,
Right.
creating these high pressure zones like at the center of a star.
Exactly.
But black holes,
Yeah.
which are, like the ultimate gravity wells,
The most extreme.
seem to have low internal pressure. Right.
So how can something be so incredibly dense and yet have such low pressure?
Yeah, it's a great question.
I mean, it feels like a cosmic riddle.
It really does.
Yeah.
And it's this seeming contradiction that makes it so interesting.
Yeah.
To unravel this puzzle, I think we need to consider this idea of informational pressure.
Okay.
And this is really about how constrained the degrees of freedom are
Okay.
in a system.
So it's not just about how tightly things are packed, but how much freedom they have to, like, do anything.
Exactly, you got it. So
Got it.
in a black hole, the matter might be crammed into an incredibly tiny space.
Right.
But its ability to move and change is also severely limited.
Okay, so it's like squeezing all the air out of a balloon.
Yeah.
Even if you keep squeezing, it's as compressed as it can get.
Exactly. That's a great analogy.
So it's this kind of like maximum information density, but minimal pressure in terms of like resistance to further change.
That's it. Yeah, it's like the ultimate endpoint of compression.
I'm starting to see the light here.
So black holes, despite their immense density, might have this low internal pressure because everything is just so constrained.
That's the idea, yeah.
Does that mean that the stuff inside is also in a state of low entropy then?
Oh, that's a great question.
Like you were saying, like a deck of cards all organized.
Yes, absolutely. That's a great connection.
Yeah.
You're absolutely right.
Yeah.
Low entropy states can be very information rich,
Okay.
not because they have more bits of information, but because those bits are organized in a meaningful way.
Okay.
And black holes are really fascinating because they kind of challenge our typical understanding of entropy,
Right.
because they seem to maximize both entropy and information density at the same time.
Wait, hold on.
Yeah.
How can something be both highly ordered, like you're saying, and have maximum entropy.
Yeah, it's a real head scratcher.
Because isn't entropy all about, like, chaos and disorder?
It is, yeah, and that's what makes black holes so interesting, is that they seem to break the rules a little bit.
Okay, so how do we make sense of that then?
Well, one key thing to remember is that the event horizon of a black hole
Yeah.
acts as a kind of information boundary.
Yeah.
And within that boundary, things might work very, very differently
Got it.
than we're used to.
So black holes are basically just the ultimate rule breakers of the cosmos.
Pretty much, yeah. It's like they have their own set of rules.
That's so cool. So it kind of reminds me of what you mentioned earlier about gravity being a sort of like a cosmic organizer,
Yeah.
right? Pulling things together into these
Yeah.
dense, information-rich structures.
Exactly.
But if gravity's pulling in all this information,
Yeah.
why doesn't it pull in things like, say, water from a high-pressure hose?
Okay.
I mean, a hose has pretty low information density, right?
Yeah.
Compared to, like, the vast, complex ocean.
Right.
So shouldn't the water be, like, pulled towards the ocean?
That's a great question.
You know?
And it really highlights how these concepts can play out differently in different contexts. So in an everyday situation like a water hose,
Yeah.
the flow is dictated by pressure
Okay.
and by energy gradients.
So it's not really attracted to the ocean's information density?
Not in the way we might think, no.
Okay.
The ocean's complexity, while vast,
Yeah.
doesn't actually have a stronger pull
Okay.
than the pressure forcing the water out of the hose.
So the ocean, despite all of its complexity, has lower pressure than the hose.
In this case, yes.
Okay, got it.
And that's what determines the flow.
So in these extreme environments like black holes, maybe information density does kind of rule the roost.
Yeah.
But here in our everyday world, it's more about like good old-fashioned pressure and energy.
That's a great way to put it.
Go ahead.
Though it's worth noting that even in everyday systems, there's still information flow happening.
Yeah.
Just not always in the way that we might initially imagine.
Right. I mean, information is kind of in everything.
It is, yeah. It's everywhere.
From the structure of matter itself to the arrangement of atoms and molecules. It's not just about complex life forms or these massive cosmic objects.
Right. It's fundamental to the universe itself.
Okay.
So even as the water from that hose mixes with the ocean,
Yeah.
its own information, its temperature, its chemical composition is being dispersed and integrated into that larger system.
So there's this like constant interplay of information, even these seemingly simple processes.
Absolutely.
So even though the water isn't being pulled like specifically toward higher information density,
Right.
there's still this kind of like movement towards greater complexity,
There is.
even at these smallest levels.
Exactly. It's happening all around us all the time.
That's amazing.
It really is, yeah.
And that kind of brings us back to, you know, another fascinating observation that I pulled from the research you guys sent,
Yeah.
which is that there does seem to be this pattern of information flowing towards higher density.
Mm-hmm.
You know, even if pressure isn't always the driving force,
Right.
it's like information wants to clump together
It does,
You
yeah.
know?
There's a tendency for it to cluster.
to form these intricate structures.
Yeah. To seek out those areas of higher density.
That makes me think about how we often use the terms density and pressure almost interchangeably,
Right, yeah. We do tend to use them as if they're the same thing.
but they're not the same thing at all.
They're not, no. They're distinct concepts.
Okay, so help me understand that.
Okay, so density
Yeah.
is really about how tightly packed matter or information is
Well,
within a given space.
right.
Pressure, on the other hand,
Yeah.
is about the outward force that that matter exerts.
Okay, so you could have something incredibly dense but with low internal pressure, like a black hole,
Perfect example.
or something less dense but with higher pressure,
Yeah,
like that water hose.
exactly. You got it.
Yeah.
They're related, but they're not the same thing.
So density and pressure, while related, are distinct concepts.
Yes.
And they each play like a unique role
Absolutely.
in this like grand cosmic ballet.
It's a beautiful dance, isn't it?
It is. It really is, yeah. Okay, so we've kind of established that density and pressure, while related, aren't the same thing.
Yeah, it's a subtle but really important distinction.
But what really fascinates me is this idea you brought up about information flowing towards higher density.
Mm-hmm.
Where does that lead us? It feels like we're kind of on the verge of something profound here.
I think you're right.
Yeah.
You're really picking up on something crucial.
Yeah.
Yeah, think about it this way.
Okay.
We see this tendency for information to cluster in all sorts of systems.
Okay.
Gravity pulls matter and energy towards black holes.
Right.
Galaxies form from this scattered dust and gas.
Right.
And even in things like, knowledge networks, information tends to concentrate in these hubs with lots of connections. So it really is everywhere.
It's like information has this kind of inherent drive to connect and build upon itself.
Yeah.
Like almost like a cosmic Lego set where the creations just keep getting more and more elaborate.
Yeah, more complex.
Yeah.
Yeah, it's a beautiful idea.
But if pressure isn't always the driving force
Right.
behind this information flow, what is?
That is the million-dollar question.
Yeah.
And I think the answer likely depends on the context.
Okay.
We've talked about gravity.
Yeah.
But there's also things like the availability of energy,
Right.
the organizational structure of the system,
Okay.
the laws of physics themselves. All of these things are guiding how information interacts and flows.
So it's like a symphony of forces,
It is, yeah.
all kind of playing their part
Absolutely.
in shaping this flow of information and this emergence of complexity.
Exactly. A beautiful analogy.
And this brings us back to the idea of a Goldilocks zone for information.
Yeah.
Like you were saying earlier,
Right.
you need a system that's rich in information, but you also need enough freedom
Right.
for that information to interact and to generate these new patterns.
Yeah.
So there's this sweet spot between too much pressure,
Right.
where everything just gets homogenized.
Yeah, like our cosmic blender, remember?
Yeah.
Everything gets smoothed out,
Yeah.
less complex,
Yeah.
and therefore lower in information content.
And then too little pressure,
Yeah,
where things are too chaotic for anything meaningful to take hold.
exactly. It's like trying to build a sandcastle on a windy day.
Right.
The structure just won't hold.
Just won't hold, yeah.
So this Goldilocks zone
Yeah.
is really where information can dance.
Ooh, I like that.
Yeah.
Information dancing.
And create something truly amazing.
It makes this like very abstract concept feel so much more dynamic.
It really does.
But it makes me wonder then, if this Goldilocks zone is so crucial
Yeah,
for complexity,
right.
why is the universe so full of extremes?
That's a great question.
We've got black holes, we've got these vast empty spaces.
Yeah.
I mean, those don't seem very just right
Right.
for complexity.
You've hit on a really crucial point.
Okay.
This Goldilocks zone
Yeah.
is not static.
Okay.
It's not uniform.
Okay.
It shifts.
Yeah.
It changes depending on the scale we're looking at
Got it.
and the kinds of systems that we're considering.
So what might be high pressure for an atom
Yeah,
could be low pressure for a planet.
exactly. You
Yeah.
got it.
Right?
Think about it. The universe on a grand scale
Yeah.
has a very low average density of matter.
Right.
I mean, there's a lot of empty space out there.
A lot of nothingness.
A lot of nothingness, but within that vastness,
Yeah.
you have these pockets of higher density.
Yep.
Galaxies, star systems, planets.
Right.
And within those, you find even denser regions, like the cores of stars.
It's like those Russian nesting dolls.
Yes.
Yes.
Complexity nestled within complexity.
Yeah.
Each with its own Goldilocks zone.
Oh, I love that.
Yeah. It's a beautiful way to visualize it.
It is, yeah.
And this is why complexity can arise and persist in such a diverse universe.
Okay.
The conditions for its emergence aren't absolute. They're relative
Got it.
to the specific system we're looking at.
This is like completely changing how I think about the universe.
Good.
We often talk about it like expanding and cooling, becoming less dense.
Yeah.
Like it's kind of winding down.
Right, like it's running out of steam.
Yeah.
Yeah.
But if we look at it through this lens of information, the picture becomes way more interesting.
It does, doesn't it?
Yeah.
It really does.
So yeah, matter and energy
Yeah.
are becoming more
As
discursive.
the universe expands, yeah.
As the universe expands, but at the same time,
Right.
information is concentrating
Exactly.
in these pockets of higher density that we
Yeah.
were just talking about.
Right, so it's like these two opposing forces
Yeah.
shaping the cosmic landscape, dispersion and concentration.
And it's that tension between the two that's kind of driving this emergence of complexity.
It's a beautiful idea.
So maybe the universe isn't winding down. It's kind of like evolving.
It's a fascinating possibility, isn't it?
Yeah. So consider this.
Okay.
The early universe
Yeah.
was super hot,
It was
super dense.
incredibly so.
Right.
Yeah.
There was like that, cosmic soup that we talked about earlier.
Right. A primordial soup.
But it was also relatively simple
It was.
in terms of its structure.
In terms of its structure, yeah. Very uniform.
Okay, so then as the universe expanded,
Yeah.
cooled down,
Right.
gravity went to work,
It did.
pulling things together,
Yeah.
forming stars and galaxies.
Exactly.
So gravity acted as this like catalyst,
It did, yeah.
creating the conditions for information to concentrate and self-organize,
Yes.
forming these more complex structures
Right.
than that uniform soup of the early universe.
Precisely.
And then within those structures,
right.
even more complex systems emerged.
Yeah, you get planets, you get solar systems, and eventually life itself.
It's like a chain reaction of complexity.
It really is, yeah.
Each stage kind of building on the one before it.
It's building upon itself, yeah.
Okay, so we've been exploring these, like, universe-sized implications of all this.
Yeah.
What about the more practical side of things?
Okay.
How can understanding this interplay between information,
Right.
density, and pressure
Yeah.
be applied in our everyday world?
That's a great question.
Yeah.
And it's one that researchers are actively exploring right now.
Okay.
Imagine being able to manipulate the information content
Yeah.
of materials
Okay.
by controlling the pressure that they're under.
Okay.
Think about creating materials with entirely new properties.
Okay.
Stronger, lighter, more durable,
Right.
even capable of, say, conducting electricity without any resistance.
No, that would be revolutionary.
It would, wouldn't it?
Yeah, I mean, but it makes sense. If
Yeah.
you can control the information,
Yeah.
you can control the structure.
Yeah.
And the structure dictates the properties.
Right. It's like having the ultimate blueprint for creation.
Yeah.
It really is.
And this goes beyond just, like, material science.
Oh, absolutely.
Think about fields like computer science,
Yeah.
artificial intelligence.
Yeah.
What if we could apply these principles of information, self-organization, to create AI that not only, mimics human intelligence,
Right.
but actually evolves and adapts in its own unique ways?
That's the dream, isn't it?
So we could create AI that's not just following our programming,
Yeah.
but actually learning and creating on its own,
Right.
potentially even surpassing human intelligence.
It's a bold idea,
It is.
but the potential is really
It's a
mind-boggling.
little scary, but yeah.
Yeah, a little bit.
But all this talk about information
Yeah.
kind of makes me wonder, are we just imposing our human concepts onto the universe?
That's a deep question.
Is information really a thing?
Right.
Or is it just a way for us to make sense of what we observe?
It's the million-dollar question, isn't it?
Yeah, what is information, really?
Yeah.
And does it exist independently of our minds?
Right. Is it out there?
Yeah.
Or is it something that we create?
Yeah.
There's no easy answer.
Yeah.
But it's a question that's fascinated thinkers for centuries.
So let's dive into that rabbit hole a bit.
Okay.
What are your thoughts on that?
Well, on the one hand,
Yeah.
we could say that information is really just a way for us to describe
Right.
and organize our observations.
Right.
We see patterns.
Right.
We create categories.
Right.
We assign meaning.
Yeah.
We call that information.
So it's like a mental map
It
you
is.
use to navigate the world.
Exactly.
Okay.
But here's the fascinating part.
Okay.
There's growing evidence that information might be more than just a human construct.
Okay.
The laws of physics themselves.
Hold on. You've lost me.
Okay.
How can the laws of physics be information?
Well, think of it this way.
Okay.
The laws of motion, the laws of thermodynamics,
Okay.
all those fundamental constants that govern the universe,
Yeah.
they represent the underlying rules of the game, the
Right.
constraints within which everything operates.
So they're like the code
They are
that the universe runs on.
precisely.
Okay.
And if we think of those laws as information,
Okay.
then information isn't just something that we invented.
Right.
It's a fundamental property
Okay.
of the universe itself.
So maybe information isn't something that we project onto reality.
Right.
But something that's woven into the fabric of reality.
It's a profound idea.
Yeah.
And if true,
Yeah.
it means that understanding information
Yeah.
is key to understanding the universe at its most fundamental level.
Okay. I think we've officially crossed over from mind-blowing to mind-altering.
It's a wild ride, isn't it?
It is. It really is.
Yeah.
This is getting deep, even for a deep dive.
I agree.
But I have to ask, if information is really this fundamental aspect of the universe, what role does entropy play in all of this?
That's a great question, and a perfect segue into our next topic.
We were just talking about how information might not just be a human concept,
Right.
but something that's like woven into the very fabric of reality.
Yeah, a fundamental part of the universe itself.
Yeah, but where does entropy fit into all this?
Mm,
We usually think of it as like a measure of disorder.
right. Randomness, chaos.
Yeah, but you were saying that there's a connection between entropy and information.
There is, yeah. And it might not be immediately obvious,
Yeah.
but it's a pretty profound connection.
Okay.
Think about it this way.
Okay.
A system with low entropy,
Okay.
like a perfectly ordered deck of cards,
Okay.
is in a very predictable state.
Right.
We don't need a lot of information to describe it
Okay.
because we already know the exact arrangement of the cards.
Okay, because we know exactly where every card is.
Exactly.
It's like in that low entropy, highly organized library.
Right, exactly.
Yeah.
But if we shuffle that deck of cards...
The entropy increases.
Okay.
And the cards are now in a more random, less predictable order.
All right.
We need more information to describe the state of the deck.
Okay.
Because there are many more possible arrangements.
So the more entropy a system has,
Yeah.
the more information we need to actually define its current state.
That's it. You got it.
Okay.
And that really gets to the heart of the connection between entropy and information.
Okay.
Some physicists even believe that entropy is the fundamental measure of information in the universe.
That's a pretty mind-blowing idea.
It is. It's a really profound concept.
So it kind of suggests that, like, the more information a system has, the more potential states it can be in.
Right.
And the more unpredictable it becomes.
Exactly. It's like the universe thrives on possibility.
Okay.
And that unpredictability, that potential for surprise, that's what makes information so powerful.
So it fuels evolution.
It does.
The capacity to kind of adapt, generate these new possibilities. Information is all about potential.
Okay, so we've got entropy and information as like two sides of the same coin.
They are, intertwined.
High entropy, high information content.
Right.
Low entropy, low information content.
Exactly.
But how does pressure fit into all of this?
Well, remember how we were talking about pressure often being associated with simpler, more uniform states?
Right.
Think about a gas that's been compressed.
Okay.
All those particles crammed together, moving chaotically.
Yeah.
There are fewer possible arrangements those particles can take.
Right.
Fewer distinct states the system can occupy.
Okay, so it's kind of like our cosmic blender analogy again.
Exactly.
Right.
You got it.
Everything gets smoothed out.
Less complex.
Less complex.
And therefore lower in information content.
But as we were talking about before, there are always exceptions.
Right.
Like those crazy neutron stars.
Neutron stars are fascinating, aren't they?
They're wild.
Yeah, they really push the boundaries of what we think is possible.
And it kind of brings us back to that Goldilocks zone that we were discussing earlier.
It does, yeah.
Where the pressure and the information density are balanced.
Right, finding that sweet spot where complexity can thrive.
So it's not just about having lots of information.
Right.
It's about having the right amount of pressure to let that information organize and interact.
Yeah, without getting squashed or dissipated.
Without being stifled.
Exactly.
It really is like a very delicate dance.
It is.
Between order and chaos.
A beautiful dance.
So this kind of interplay of information and pressure.
It's really fundamental, isn't it?
It might be a fundamental principle behind the emergence of complexity in the universe.
It might be the key.
From galaxies and stars.
To planets.
To planets. And life itself.
And everything in between.
It's a pretty awe-inspiring thought.
It really is.
That complexity is like a fundamental feature of the universe.
Yeah.
Not just a random accident.
Right. Not just a fluke.
But an actual consequence of how information...
And pressure.
Pressure and all those fundamental forces.
Yeah, it's all connected.
All kind of tango together.
A beautiful, intricate dance.
So where is all of this leading?
That's the big question, isn't it?
Yeah.
I wish I had a crystal ball.
Yeah.
But unfortunately, we don't really know the ultimate fate of the universe. Yeah. But based on what we understand about physics right now, there are a couple of possibilities. Cool. One is that the universe eventually reaches a state of maximum entropy. Often called the heat death of the universe.
Heat death?
Yeah. It doesn't sound very appealing, does it?
No, it doesn't.
No.
How would that even look like?
In that scenario, all the energy in the universe would be evenly distributed. Everything would be at the same temperature, and there would be no more potential for change or for new complexity to emerge.
So like a cosmic lukewarm bath?
Pretty much, yeah.
No more stars, planets, life.
That's the basic idea, although the details are still being debated.
Right.
But even if this is the ultimate fate of the universe, it's likely trillions upon trillions of years in the future.
Oh, okay. So we've got some time.
Yeah, we've got a bit of time to enjoy the show.
But what about the other possibility?
Yeah.
Could the universe keep getting more complex?
It could.
Even as it expands and cools.
That is definitely a possibility, and there are some really intriguing theories out there about how that might happen.
Wait, really?
Yeah.
How could, like, expanding and cooling lead to more complexity?
Well, as the universe expands,
yeah,
the distances between galaxies increase.
Right.
And the overall density of matter goes down.
Right, right.
But at the same time,
yeah,
the very fabric of space-time itself is stretching.
Oh, okay.
Creating more space.
More space for what, though?
Well, some physicists believe that this stretching of space-time could create new possibilities for information to organize itself, leading to the emergence of entirely new physical laws, new particles, even new dimensions.
Whoa, okay.
It's pretty wild, isn't it?
New physical laws.
Yeah.
New dimensions.
Yeah, who knows what's out there?
It's like the universe is constantly reinventing itself.
I think that's a beautiful way to put it.
Yeah.
We live in a dynamic universe.
We do.
Constantly changing, constantly evolving.
Yeah.
And this interplay of information, pressure, and these fundamental forces might hold the key to understanding that evolution.
I think we have officially reached, like, peak mind-blowing for this deep dive.
I think you might be right.
We've covered so much ground.
We have.
From black holes to the heat death of the universe.
So it's been quite a journey.
From the emergence of complexity to the very nature of information itself.
All thanks to those amazing questions you sent in.
Yeah, so thank you guys so much for sending those in.
Absolutely. Keep them coming.
Who knew that pressure, information density, and gravity were so deeply intertwined?
It's all connected.
With this grand story of the universe.
It really is, yeah.
So to all of our fellow knowledge adventurers out there, keep exploring.
Keep questioning.
Keep questioning.
I'll keep diving deep.
And keep diving deep into these mysteries of the universe.
Absolutely.
Until next time.